Okay, so this talk, was originally supposed to be a much longer talk with more, involved example. I wanted to work out, building an interpreter in Haskell or something. And then realizing that it was going to be from 7:30 to 8 and, nobody was showing up, it turned into, I'm going to talk about basically what Haskell is, what functional programming is, and then give you a bunch of, code snippets. So, I'm going to start with Project Euler. Have people heard of Project Euler? Yeah, it's a bunch of, math problems that you can solve, with code. So this is a particularly nice one. That was one of the first ones I did when I was first learning Haskell. So you've got a Pythagorean triplet, which is a set of natural numbers, a less than b less than c, that you can make a right triangle with them, right? So the problem is that there exists exactly one Pythagorean triplet for which a plus b plus c equals 1,000, and you want to find the product of those three numbers. So this is how you do it in C. You've got this sort of nice looking nested loop thing. It's okay. Here's how we can do it in Python, which, this is really ugly Python, I think. I don't know. I don't do enough Python. It's sort of ugly, though. And here it is in Haskell. It's basically almost exactly like the Python solution, but that's because Python stole their list comprehensions from Haskell. So, but it's basically the same. So, these square brackets, we're creating a list of, a times b times c for c is in the range of 0 to 1,000, b is in the range from 0 to c, and a is in the range from 0 to b, such that a squared plus b squared equals c squared, and a plus b plus c equals 1,000. And the head function just pulls off the first thing in the list. So what's Haskell? Haskell is a programming language which is purely functional, statically typed, polymorphic, and lazy. And I think I've got slides that cover all of these things, but I'll get back to those in a minute. So functional programming, functional language is usually characterized by the primary things having functions as values. They're not special like they are in C. You can pass them around as data like you can numbers or booleans or whatever. Usually immutable data structures, although this isn't a strict requirement. But going along with that, we usually want to avoid mutable state because that causes a problem with concurrency and sort of things. Makes reasoning about code a little bit harder. And we usually push recursion instead of loops. Haskell doesn't really have a looping construct. Most functional languages don't. Okay, so the Haskell wiki lists 3 features of functional languages, which are usually higher order functions, which are functions that can take other functions as arguments or return them as the evaluation of the expression. Purity means that your language has no side effects. So now you're probably thinking that a language that doesn't have side effects, we can't print or modify some database or something. That's probably not very useful. Haskell gets away with this with these things called monads, which I sort of understand, not completely. It's sort of a big buzzword. And recursion is usually another thing that characterizes functional languages. So just when you have a function that can call itself recursively. So types. Every value in Haskell has a type. So numbers can be integers or floats, and those are specifically different from each other. They're different from each other in C too, but they're not as critically separated from one another as they are in Haskell. Static typing means that all types are known at compile time, so the compiler is able to do all sorts of optimizations based on the types of your data, of your functions, etc. Strong typing, this is almost ripped straight from the wiki page. But there's fine-grained sets of types that they're very definitively distinguished from one another. In C, booleans are basically just 0 or non-zero, right? So in Haskell you've got true and false, and those are not numbers, they're just true or false. They're bools. Polymorphism, Haskell supports 2 forms of polymorphism. One which is parametric polymorphism, where we have data types that are parameterized by type variables. I have examples of this, which will hopefully explain it better. And ad hoc polymorphism, which is sort of operator overloading, I guess is the best corollary to it in object-oriented languages, where a value can adopt one of several types based on literally different definitions for. I guess the easiest example is the addition operator in Haskell is specialized for there's a different definition for like integers and floating point, etc. Laziness. Laziness refers to a non-strict semantics and sharing. So expressions aren't evaluated right away. They're only evaluated when you actually need the value of that expression. And Haskell uses, or at least I think it uses like in the background, like a graph structure that tries to optimize like where such an expression is used and gives that to all the places that it's needed. So today's talk, I want to talk about like the absolute basics of Haskell. I want to talk about lists. My outline is sort of bad. These are the things I originally wanted to talk about. I'm not sure I actually cover all these things or don't cover all of them, but I want to get you like a taste of the basics of Haskell, what lists in Haskell look like. Very basic examples of polymorphism and pattern matching. I focus a lot on pattern matching, but things that I don't want to talk about, type classes in much depth, and monads. So this is what hello world looks like in Haskell. You've got main, which is, so double colon means main has type IO unit, and then we're defining main to be put Sterling hello Haskell. This is what hello world looks like. The IO unit thing, the two parentheses are pronounced like unit, says that like this function, it's not really a function, this value lives in the IO monad, and this is how like Haskell gets away with like side effects without like having the trouble of mutable state, etc., etc. Okay, so types. Every value has a type. So like at the top we've got a list of characters. ABC has type list of char. List is just represented the same way as the values are represented with square brackets. True has type bool. Put Sterling has type string to IO unit. Main usually has type IO unit. I'm pretty sure it always has that type, but don't quote me on that. Map is a function which takes another function from a type A to a type B, and then also a list of things of type A and returns a list of type Bs. So it takes a list of things and a function that takes those things and turns it into other things and gives you a list of the other things. Does that sort of make sense? The thing is, like, all functions in Haskell really only take one argument because functions are curried automatically. I don't really have a good explanation for that. So filtered is a thing similar to map. It like applies a predicate, a function from like a type A to a bool, and then filters out all the things that like don't satisfy the predicate. Fold R and fold L are sort of like accumulator things. They'll like do some operation on the elements of the list and like accumulate them into like another value. And fold R and fold L, the main difference is that fold R like does its operation associated to the right, and fold L does its operation associated to the left. Okay, algebraic data types. So we can define our own types in Haskell. So like we can make a binary tree super easy. We do data bin tree A is a node is our constructor. So here's where we've got like parametric polymorphism going on. The A represents some type. We don't know what it is yet. I should have given an example of like actually instantiating this, but so we have like we could replace A with any concrete type, like an int or a list of ints or anything. But basically we've got like a node which has a value A and then like a left tree and a right tree, right? Or it can be empty. So some common types in Haskell that are used all the time are the maybe data type, which is either just a value or nothing. I'll give an example with maybe later. And then the type keyword, as opposed to the data keyword, defines a type synonym. So at compile time, like something like data bin tree creates like a whole new data type. It makes like a storage space for it and whatever. But like at compile time, type synonyms like string to list of char are all replaced with instead. So it won't be string; it'll be list of char at compile time. And you can make all sorts of type synonyms. Sort of like type def in C, but not as messy. So lists, we can have lists like 1, 2, 3, 4, 5. It's a list of ints. Hello is a list of chars. and the hello string is the same as the list of the individual letters. We can have ranges like I showed in the Project Euler example. So 1.5 is just the list 1, 2, 3, 4, 5. And because Haskell is lazy and doesn't evaluate things right away, we can make an infinite list, 1 dot dot, which is just 1, 2, 3, 4, 5, et cetera, et cetera, et cetera. More lists. So we can apply functions to lists. So I can define a function inc items, which, so this num a thing is a type class. And so the num a in parentheses followed by like the equal sign and arrow means that we're requiring that the a implements like the num interface, which defines like plus, minus, times, and maybe a couple other things. So inc items of ls, we just are going to map over +1, and +1 like that is an operator section. So it's literally a function that takes a value and adds 1 to it. We can define anonymous functions called lambda functions with a backslash the variable, and then whatever expression we want that to evaluate to. So we can define a squaring function by like lambda x to x times x. And then we can make a function that squares the things in a list by doing squares as map square. So with laziness, we can do things like say let x equal 1 over 0 in 5, and that'll evaluate to 5 just fine because we don't ever need the value of x, so it never tries to evaluate it. And we can do the Fibonacci numbers in one line with 0. Oh, the single colon is the cons operator. So it's an infix cons operator, which takes an item and a list of things of that same type and gives us a new list. So this is basically like, also zipwith takes two lists and it zips them together like applying a function to like the matching pairs. So like if we had two lists of just integers and zipped them together
May
with
I
plus.
have your attention, please? The time is now 7:45, and the library will be closing in 15 minutes. Thank you.
Okay. So zipwith will take like two lists, and this will take the two lists and add them together like pointwise. So tail rips off the first thing of a list and gives you back the rest of it. So what was happening is we've got like 0, 1, and then the tail of the list starts at 1. So the zipwith will have 0, 1. The next thing will be 1. So we've got a 1 plus a 1. Just, you could write it out. I didn't, but if people are interested, ask me after. Okay, so we can do pattern matching on literals. So we can define a function is5 from integer to bool by saying is5 5 is true, and is5 underscore means we don't care what that argument is, so we're just ignoring it, which means like is5 for anything else is just false. We can do case analysis, so do a function like bool to int with type bool to int. So we do case b of, so bool to int of b is case b of, if it's true, we evaluate to 1, if it's false, we evaluate to 0. And bool has no other values, so it's a perfectly good function. And we want to do like patterns on pattern matching on lists. So here's a definition of head, which I think is almost exactly the same as the standard head function. I just call it head prime because it's not head. So it takes a list of things of type A and returns a thing of type A. 2 square empty square brackets is an empty list. So head operating on an empty list is error empty list. Error is a special function which has like type string to A, whatever you need it to be. So that's how we get away with that. And then this other thing is a pattern match on, so lists can be constructed in two ways, and there's like some syntactic sugar on top of it. Either a list is either an empty list, or it's an item cons a list of items. So xcons xs says that x is at the head of the list, and then xs is the rest of the list. So head of xcons xs is just x. Adding in patterns and types, we can write a safer head function that won't like throw an exception with safe head from type list of A to maybe A. If we get an empty list, we just return nothing, and otherwise, this won't actually type check because x isn't of type maybe A, x is of type A. So there should actually be a just in front of x, which slipped past me because I couldn't figure out how to make my slides also be a compilable module. So type classes like arise really early because like all of the numbers in Haskell are polymorphic of like num A type. So addition operates on things that implement the num interface. So plus takes two things of type A and returns another thing of type A, but that all have to be like resemble numbers. Same thing with minus and times. I said I wasn't going to talk about monads, but it's a decent example of like what the definition of a type class looks like. So we can define a type class, we give it a name, so class monad M, where M is whatever our monad is, where, and then we give the types of the functions that we want the type class to implement. So this first thing is called bind. It has type MA to A to MB to MB, which doesn't really matter if you don't understand it. Same thing. The next thing is just bind, but without actually caring about the first argument. And then return and fail. So the idea is that M will be replaced by a data type, and we can see that if we implement it for maybe. So to implement a type class, we do instance monad maybe where, and then when we have infix operators, we can define our own infix operators. We can actually write a definition for it as the infix. So just a bind f is just fa. Nothing bind anything is nothing, and return is just. And I don't actually need the arguments because just sort of doubles as a function from types A to maybe A. I think that's the end of mine.
So my only experience with Haskell was trying xmonad. And unfortunately, I didn't get very far with it. And then I started looking into Haskell, and then I didn't want to ruin my perception of Python. I don't know. How do you feel that Haskell measures up when it comes to just being an everyday scripting language compared to Python or Perl?
I don't think it gets like a lot of use like as a scripting language as opposed to like Python and stuff.
Mm-hmm.
It's most often like compiled and something like that. But I don't know. I haven't done like too much in Haskell, but like my first like real programming class in college was in Haskell, so I have like a soft spot for it somewhere.
Mm-hmm.
And like I'm interested in like programming language research, so I still like mess around in Haskell from now.
Well, it's sad to hear that Python stole its comprehensions from Haskell. It's one of my favorite things ever.
Why is that sad?
Well, it's not sad at all. It's
Oh, about my
it just
Project
makes me
Euler
feel
thing?
like I should pick up a Haskell book at some point.
Oh,
And
I was supposed to have like a references slide at the end, and then I ended up forgetting about it. But there's like a ton of like free resources to learn Haskell. Learning a Haskell is good. It's free. It's very beginner oriented. There's lots of cool cartoons in it, but it's free. I think it's like learnyouahaskell.com or something. But Google for it. Also, Real World Haskell is also free and online. Some of the things are out of date, but Stack Overflow is a good resource. Haskell mailing lists, etc., etc. Yeah.
For someone who hasn't used Haskell, can you give some real-world examples of places where the language is especially strong, where there are things intrinsic to the language such as laziness, would cause it to be a much better choice than other languages?
I'm trying to think if I know places for sure where Haskell's applied. I don't know off the top of my head about Haskell, but like OCaml is a similar language. It's not actually lazy, but Jane Street's like a trading firm in New York, and like all of their software is written in OCaml, which is also a functional language, but different from Haskell in the sense that it's not purely functional and it's not lazy. But like a lot of the theory applies, and they do a lot of I guess like the advantages of languages like Haskell are you can reason a lot better about like the source code because you don't have mutable data structures, you don't have like side effects that can go happen like any which where. So like concurrence, like you can do concurrency a lot easier because you don't have to worry about like threads competing for like something that can like change like all of a sudden.
And what would you consider to be the language's greatest weaknesses?
Weaknesses, I haven't personally had a lot of problems, but like a lot of the complaints that do come up are like laziness makes reasoning about like space usage really hard because you'll build up like thunks, like unevaluated things that like may or may not ever get evaluated, and that makes it hard to reason about space issues.
I see a lot of use in just plain math. The way that it was handling those comprehensions, ranges, everything else like that, it makes doing a lot of the things that I actually do on a day-to-day basis a bit easier and faster to write out. It just takes me learning Haskell first. So, but that's impressive and amazing right there.
It's fun stuff.
And then the Fibonacci sequence in one liner is ridiculous. I love the ability to make recursive stuff without ever actually calling a function. So, well, calling it, but not calling
But
it.
yeah. See, that's the other thing with laziness is like you can call your functions right away because like it's not defined yet, but that doesn't matter. Like it gets defined, it builds it up as it goes. But I didn't actually run like time on any of these, but the C solution terminates like instantly. Python runs not like too long, but like a minute maybe. Haskell's slower than C, but still much faster than Python, I found. And also this was interpreted Haskell, like I ran it in GHCI, which is the Haskell interpreter. So I'm sure if you like compiled it with
May I
optimizations,
have
it
your
would
attention,
be much
please?
faster.
The time is now 7:55, and the library will be closing in 5 minutes.
Well,
We
thank
ask
you,
that you
ma'am.
please use all computer and laptop work and exit the building at this time. Thank you.
And out.